question from Group 1, and I was doing item 1 for the final exam. Okay, from what item 1 is asking us to sketch the behaviors of the following equation that were given. As s goes as the limit of x approaches to 5 on the positive side, f of x would be negative infinity, as that's shown here. God, that was awful.
It's okay.
And as is approach 5 on the negative side, it'll be approaching positive infinity. And this will work vice versa. So as s of x. Actually, yeah, I'm on the right track.
No, you're good. You're good.
I know. So as x is approached to negative infinity, it will be 5. As the limit of x approaches to infinity, it will be negative 5, as shown here.
Item 10, you're linearizing the square root of 2 minus x and to approximate the square root of 1.9. And this whole thing is to show, how she phrased in class, appreciate how people did this before calculators.
Mm-hmm.
And it's basically, you get the derivative to get the slope for your linearized line, plug in the a that you're given to get, plug in the a into the derivative function to get the slope of your linearized line, and then you plug in a again into the original function to get the point of, for the linearized function, and then you slope plus point equals the linearized line, and for the linearized line you plug in 1.9, and how did she phrase it? Appreciate how we did this before calculators. And she's like, guys, this is how it was so smart. They were so smart figuring this out.
Yeah,
Which is calculated.
They were geniuses for it.
Yeah.
Because, like...
Geniuses, that was the word I was trying to think of.
Yeah.
Yeah. Is that good?
Yeah.
Okay.
That's fair. So we have to find the critical numbers of this graph here. And critical numbers are basically points of tangency where the slope is either 0 or undefined. And so just by observing the graph, we can see that, here's 3, our slope is 0 here, very obviously. There's no confusion about that. Same with 6. So that's why we have x equals 3 and 6. See, for 4, this slope is undefined. And so that's also a critical point. And then here, after some research online and stuff, I wasn't sure whether or not that counted as a slope being undefined, because if it's discontinuous, that leads to questions. And so I just looked it up. I think I discussed this a little bit with Team 2, and we came to the conclusion that regardless of the fact that it's discontinuous, as long as there's a function value, then the slope is undefined. So that's why we got 3, 6, 4, and 2. And then, if you just look at all the other points, there are no points where it's 0 or undefined. And you don't include endpoints or critical numbers. They have to be they have to come from both directions, so you can't do the endpoints. So yeah.
Okay. For question 14, it provides the equation of the boundary will provide with the boundaries of the area determined by the given interval, while x is less than 0. from what we can tell, the top would be f of x, the bottom would y equals 0. The x's for the left and right would be x equals a and b respectively. As for how it will look,
Right, so like how do you know that the right bound is x equals b? And how do you know the left bound is x equals a based on this definite interval right here?
good question. That's a good question.
Do you know?
Well, the first way to figure out it is to graph the thing on Gizmos. The other is to find the
Well, we
derivative.
don't have an equation. So this is all theory.
Mhm.
You know, so say that this was an equation. Say that b had a value and a had a value. How do we know that b is going to be the right side of our geometry and a is going to be the left
Well, I
side?
mean, look at the defined integrals that were given. Since x is equal to a on the bottom of this, which is located here, it stands to reason that it had to be a number lower than b.
That's right. And so that's why x equals b is going to be representative of the right side.
And x equals a represents the left.
And then,
As for
yeah, why is the bottom y equals 0 and the top fx?
look at it this way. As f of x is, well, whenever f of x is greater than 0, that would be our top. so it stands to reason that 0 would be the bottom. As for
And you're saying f of x is the top?
whatever value is in f of x.
Well, yeah.
But from what we were given, we don't know what f of x will be.
Well, f of x is a function.
Or whatever
So-
that's in that function.
Yeah. So it'll be a line that, you know, b and a will connect to, and it'll create sort of the balance for the box.
Exactly. So whatever f of x connects to both a and b, that will be our top.
Right.
As for 0, it will be our bottom.
Yep. That's good. Do you want to draw like a little
Yeah, I'm
diagram just to
Yeah.
and you can just make the function arbitrary.
Yeah, the next question is basically drawing a diagram, but it's a different
It's a
equation.
different one? Okay, well I was thinking if you wanted to draw a diagram for this one just to further validate it, but it's up to you.
Oh yeah, I'm validating this. Okay. But okay.
And then draw the top one.
This picture is that bead looks ugly.
You can use your hands by the way.
Good to know.
Might be easier.
Oh god, that's even worse.
It's fine, just
It's
see, that's a B.
Anyway. These points will represent A and B. As for the graph, pretend we had something like this. Ugh. I know, not my best work.
No, it's fine.
So
But the thing is that our f of x is greater than 0.
oh wait. I should probably fix that. It probably should look more like this. And no, that's even
No,
worse.
that's good.
You know where I'm going with this.
Yeah, I get you. Perfect.
That would be our f of x.
That whole line, you mean, would be f of x?
Yeah.
Yeah, okay.
And as for this bottom line, that would be our bottom.
That's right.
Hey, Madeline. So this is Emily. Validating item 15, it asks you to provide a graph of the bounded region determined by the definite integral. So if you go ahead and look, it's given an integral with the bounds, the right boundary of x equals 2 and the left boundary of x equals 1. So we drew a dotted line on x equals 2 to just kind of see where that would be. And then we did the same thing with x equals 1. So those are our interval kind of area that we're looking at. And then the formula or the function that we're looking at is e to the x. So e to the x dx, so we drew the e to the x line curve. And the area that is bounded, it would be along the x equals 1, the x equals 2, the bottom would be y equals 0, and our top boundary would be the curve of the function, which would be y equals e to the x. So just kind of like Christian mentioned up here, you can see that this part of the equation equals the right boundary. This part of the equation equals the left boundary. And it hits along the x-axis, so where y is 0. And where for our top boundary where y is the curve. The bottom boundary was because it only goes up to the x-axis line. So where y is 0 is where the x-axis is.
Yeah.
Right?
Yeah.
Okay. So for this one, we originally did it wrong. So we drew the top boundary, the bottom boundary, and the bounds on the left and right using the two functions and the boundaries provided for the integral up here. So x equals pi, x equals y equals x, so on and so forth. We originally did the wrong rectangle. We've realized that now, and Dylan's going to explain how to do the right rectangle. But we originally did this large rectangle because we assumed that, or I assumed, my fault, that when we were talking in class about approximating a rectangle, we talked about having the whole area and then dividing it up into slices of rectangles, and each of those slices is change in x wide. You know, you choose an arbitrary width. So I just assumed that we needed to have the typical approximating rectangle be the whole area of it with a right boundary, or with a right boundary.
Yeah, right boundary.
Yeah, a right boundary to
As the height, yeah.
as the height, and then the width, obviously, the width between the two left and right boundaries. But Dylan's going to explain how we were actually supposed to do it.
Okay, so the approximating rectangle is actually supposed to be the sort of average area of, you know, a given rectangle within the whatever change in x that we choose. For this one, it's just, you know, this is going to be our change of x down here. It's our width. And then our height is just going to be the midpoint in between the two. So, you know, I guess if we wanted to label it, we can label this h for height. And we can label our change in x width, w for width. We can say that is equal to change in x. And yeah, it's just a very basic triangle, or rectangle. And then just to explain how we got like this shape, we just plugged the functions into Desmos, and then, you know, obviously that creates two lines, and then we just connected that with our x equations, and it gave us the shape here when we just shaded that. So yeah, that's it.
Mm-hmm. Okay, so this is item 1 from part 2 of our validation. First we had to declare variables from the problems. So let me just show you the problem. In 46 here, we had to declare that m was the mass, m naught was the mass of the particle at rest, And then v is velocity and c is speed of light. So those are them declared up there, except we had to add in some other ones from the other problems, but that's all that matters for 46. So I'm just going to read you what I wrote, and then I can go in and explain what we kind of meant. In item 46, we were in chapter 2, section 2, which was all about the limit of a function. We were learning how to graphically and analytically and from a table find if a limit exists at a point on a function. So we were basically just seeing different methods of finding limits, whether you were looking at a graph or we were looking at a function, like an equation. In this problem, we discovered that as v is approaching the speed of light, the denominator, don't know why that wrote, anyway. In this problem, we discovered that as v is approaching the speed of light, the denominator approaches a 0 value. So that's because, as you can see up here, v is divided by c. So if v and c are approaching the same number divided by itself is going to be 1, and we have 1 minus that. So 1 minus 1 is 0. So as you're approaching, so v is approaching c, the denominator is approaching a 0 value. We knew from one of the rules in our flashcards and by logic that as a denominator approaches 0, the quotient of the equation, in this case the mass, becomes larger approaching infinity. So again, that's just from logic. If the denominator of something is approaching 0, as it gets closer and closer to 0, it's getting closer and closer to a very large number as the product of it. And then this helped us understand a practical use of limits and wrap our heads around a function or a relationship that can cause our product to approach a value as one of our other values approaches 0. So we were just kind of using this as an example to understand one of those basic functions in calculus of how limits work. So that's the answer. So m is approaching infinity and getting larger and larger as v approaches c.
What's the specific idea of the limit?
Start on the first one, so the variables and parameters.
Okay. So the variables that we got here are L, L0, or L, L0, and 1 minus v squared divided by c squared. Did I get that correctly?
Mm-hmm. So the variable is like
No, wait.
things that are changing.
No, wait. Okay, forget that. Forget that L. Alright, forget that L.
No, that's a variable.
Oh, wait.
Well,
thinking I'm starting to get confused.
It's the product,
It's
which
a
is
product.
a variable.
Yeah,
So forget that
It's-
part.
yeah, so
So,
what are constants? Start with that.
constant will be c squared, right?
That's one of them. It's the other constant.
V squared?
No.
No, L.
No, wait.
L not.
L naught?
Yeah.
Because that's L at rest.
So that's not changing. And c, the speed of light, isn't changing either. The velocity is our main variable for this equation.
Ah, gotcha. I'm guessing that one is also a constant.
V? No, V is
One.
not a constant. Oh, 1? Well, yeah, because it's just 1. Yeah, so, I mean, you have, so those are our variables and parameters. And what do we learn about limits in this problem? Like what? Do you understand the problem? Or?
So, what we understand,
Would you like to see our work?
yeah, because I still have my head around it, but
Here's our work.
okay. In item 54, how we learn about limits and how we understand it is located in section 2.3, when we learn about limit laws and how to use them accordingly. And in this problem, when we given L naught, we're given the Lorentz concept formula. This is similar to the last problem that we did as v is approaching the c. As this function comes closer to equaling 1, but when I see the function itself, and also being square rooted by the value multiplied by L naught, which is also approaching to 0. This will make it smaller and smaller, because L naught is a constant multiplied by a number going smaller will make the product. Like the product length goes smaller as well. So at we're getting closer to C, the left length goes smaller and smaller as it approaches to 0. From the left of it, the left matters become its velocity as it approaches the speed of light. So we don't know anything about, so far, we don't know anything about a velocity faster than the speed of light. So this is coming from the left.
Yeah.
That's all right.
Okay. For item 2, I'm going to explain part A, and I'm going to switch off with Cass. We're going to explain this one together. So first, we want to declare all all valuables. We want to declare all variables and parameters with appropriate units so that we can solve the problem. So we are calculating our acceleration according to time. Oh, here it is. Okay, good. So we have position as in meters for our P. Oh yeah, sorry, I'll show our work. Okay, we have our position represented by P, and it's going to be in meters. We have our velocity represented by V in meters per second. Our acceleration represented by A in meters per second squared, and our time T in seconds. So for this problem, our parameters are going to be, we're given the time between 0 and 8. They're all variables. There you go. Okay, Cass is going to explain B.
Okay, so for B, we're given acceleration, and you have to find velocity, which is the integral of acceleration. So you just, is that it? Yeah.
You just integrate it.
Yeah. And then you plug in, you're given V of 0, so you can find C. And V of 0 is just 0t times something minus 0t or something plus C. So V of 0 equals 36, so 36 equals C. And that's how you get C for the velocity function. Why did I draw? I'm sorry, I didn't mean to draw. Okay.
You can scroll with your fingers if you need to see the problem. No, scroll with your fingers on the pad.
Your laptop's weird.
Yeah.
Okay.
So what are you doing, Zena?
Yeah, pretty much.
C is...
Okay. I'm explaining part C. It's what is the velocity after 1, 3, and 7 seconds? What do these velocities imply about the motion of the particle? So here you can see that to calculate for 1, 3, and 7, we plug 1 in for V of t, which we already calculated that formula. V of t equals 3t squared minus 24t plus 36 over here. So all we do is plug in 1 for all of our t's, and we get 15 meters per second. Then we go ahead and plug in 3 for all of our t's. And once we do that, we get negative 9 meters per second. Then we plug in 7 for all of our t's, and we get 15 meters per second again. So that's our velocity at those times. The velocities are implying that the particle initially moves right, then left, then right, because it's going in the positive direction, which we're just assuming is right. It could be any direction, but it's moving in a positive direction, and then it's moving in a negative direction, and then it's moving in a positive direction again. So, there you go.
And then for D, it's asking when the particle is at rest. So we just used Desmos, plugged in the velocity function, and just looked when it crossed the x-axis, which was at 2 and 6 seconds. So before it was at rest, it was moving positive, just slowing down, and then at rest. And then after that 2 seconds, it moves left, speeding up, and then it slows it back down to get 6, where it's at rest again, and then it moves positively again, which we define as right, which is completely arbitrary because you choose which direction is right and left and
Which is
positive
positive,
and
negative, yeah.
Yeah.
But usually positive is associated with the rightward direction.
Just depends on how you define it. And then we're only supposed to do D. Oh, E.
Yeah. Okay. Part E asks, when is the particle moving forward? That is in the positive direction. So again, we assumed that the positive direction forward was going to be to the right. So we say that the particle is moving forward when the velocity is positive from 0 to 2 seconds and after 6 seconds. So again, this was calculated all the way up here, and we could see it in our Desmos graph, that from 0 to 2 seconds it's moving in the rightward direction or the positive direction, and then it moves back from 2 to 6, and then after 6 it's moving forward again. So there you go, that was that problem.
Okay, so this is going to be item 3, or part 2, item 3. So it's the rocket problem again, although we're asked like different questions this time. So address the exercise above, explain the meaning of the Riemann sum that you use to address this problem. So the Riemann sum is the sort of the sum of the areas of the rectangles that we get when we're trying to evaluate the area under the curve. In this problem, the delta x is going to be different based on like where we are time-wise in the launch. So in order to get the Riemann sum, we have to. So normally we would like take all of the heights of the rectangles. At the say we're doing right point evaluation, it would be the height of the rectangles based on the right side of the rectangle multiplied by a uniform change in x. But because our change in x is different, we have to do the height on the right times its individual change in x, and so on and so forth for the rest of the number of rectangles that we have. And to get an approximation for the height, like the actual height of the rocket at 62 seconds, what I did, and I'll show my work here, was I took the right endpoints, and maybe it would be helpful to have like a visual here or something like that. But basically, I can just draw like a little thing here. So say that we have our, and the function looks something like this, and then say that that's 62 seconds. So in order to do, I don't know, let's say that that's my height there. And we have another rectangle, another rectangle, another rectangle. These are not perfect by any stretch of the imagination, but bear with me. So for the right side evaluation, we're taking the heights as this here, the right side of the rectangle, which would be represented by these, what do you want to call it, multiplication thingies here. Yeah. Products, there you go. So say that's 0, that's 10, and so on and so forth. Say this is 185. And we just take the sum of the products, or sum of the areas rather, of all of these rectangles. And that'll be what we get for the approximation for the height of the rocket at the 62 seconds based off the right endpoints. But if we want a more accurate estimate, then we have to take the left endpoints as well, which is given by the summation of these products here. And we get a different value, a 31,000 and change. And so what I did was I just took the average of the right endpoints and the left endpoints, or the approximation for the area under the curve given these sort of heights of these rectangles, and I got 43,293.5 feet.
What about the midpoints?
The problem with doing the midpoints in this problem is that we're not actually given a function. We're just given like values here. So we could, so we could like maybe try to guess what the midpoints would be, but based on the fact that we don't actually have the function values at those midpoints, it's better to do the average of the right and left endpoints.
That makes sense.
Yeah. And then, let's see. Okay, I think that's everything for, and that's just me explaining the Riemann sum. And then for B, all I did was I went on Desmos, I put in a table. I think I actually attached it to the end here. Yeah, so I put in a table. In my camera. So I put in a table here, which gave us, gave us our points, and then I did the line of best fit, which is the given by this here, and then to get our third-degree polynomial equation, when you do the line of best fit, Desmos will give you sort of values for, in this case A, B, C, and D, and then we can replug those back in to like a new function, which I made in red, and it gives you an equation for the line, basically. And so that's how we got that. And then Cass is going to explain part C, which is where on the test, we actually, our approximation wasn't like fundamentally wrong, but we didn't do it in the way that you wanted us to do it. So we have it written on the board here, what we should have done, and then you can kind of also explain what we did do, which was that we did basically what we did for 62 seconds, except we just added on 125. And what we should have done was use the fundamental theorem in calculus, which will explain.
So in the actual exam, you just added f of 125 when you should have done the integral.
Yeah, so basically I just
thing.
did the right and left endpoints, except I just included 125.
Okay.
And I shouldn't have done that. What we should have done was
The
use
the line of best fit that you got,
the line of best
get
fit,
the integral of that,
take the integral
do the f of 125 of the integral minus the
of
f
it.
of 0.
Yeah, because that's the fundamental theorem of calculus. And then that'll give us a new value, which is going to be more accurate.
If you don't do that, you might get a completely different result, right?
Our result wasn't like super different. On the test, we got 219,000. And with the fundamental theorem of calculus, we get 206,426. 0.9594 feet. So
It's important to make sure you include those little details when doing stuff like this.
yeah, I mean, when I was when we were taking the test, I was like, interesting that we're not using fundamental theorem of calculus on this entire test, but in hindsight, we did. So it was just didn't properly read the instructions, but
So the equation that you put here is the line of best fit,
that's the line of best fit.
and then you take the integral of that.
You take the integral of that, which we have written on the board here. We evaluated that C is 0 because there's no initial position.
Yeah.
This probably your official PSA tip. Make sure you read the instructions in its entirety.
Yes. A valuable public service announcement.
And then the f of 125 minus the f of 0 is just the,
Capital
the-
F of 125 minus capital F of 0 is...
it's just like the b minus a
Yeah.
thing that we do with regular integrals.
Um,
Well, not regular integrals, but like
definite. Well, yeah.
definite integral process we would do on like an exercise sheet.
Basically, yeah.
Okay.
So yeah, that'll give us the area under the curve, and once again, our answer was 206,426.9594, and that'll be like our more accurate, height of the rocket at 100
So
in
you're only
25
like
seconds. I was off by like
13,000.
13,000. Yeah, but I mean, it's not that much. But
I mean, it's a lot if it's
A rocket.
yeah,
yeah.
like 13,000 feet is the height of like.
I like to think that I was 1% off or 2% off.
That's a good way to think.
It's a good way to think.
2% error.
2% margin.
That's right.
Yeah.
Hi, Madeline.